Good day everyone. Today my group and I from section 4 group 12 will be presenting on the topic of the double intersection Warren Bridge. First, let me introduce our guide for this project, Encik Khairunnizam bin Ngadimon, who has been instrumental in helping us understand the concepts behind this structural system. Our presentation will cover the design, structural efficiency, applications, and conclusion regarding the double intersection Warren Bridge. Let's dive in and explore why this bridge design is significant in the field of engineering. Thank you, and let's begin. Before we move forward, let me introduce our team members who have worked together on this project. First, we have Sukri Srisu. Next, Gugan. Following him is Harishan. And lastly, myself, Yashwindran. Together, we have collaborated to analyze and present our findings on the double intersection Warren Bridge. Now, let's move on to the main content of our presentation.
For introduction, the double intersection warrant, or more known as double intersection warrant truss, is a type of structural framework used in bridges that consists of a series of repeated equilateral triangles. The primary characteristics of a warrant truss is that it only uses only diagonal members to form triangles, with no vertical members that cross each other in the basic design. The design is efficient in terms of distributing loads or forces across the whole structure linearly. In a double intersection Warren truss design, the diagonals cross each other at 2 points, creating a more complex pattern of intersecting triangles. This can provide additional strength and stability to the overall structure.
Alright, for background of case study, the double intersection Warren task is an advanced version of the 1848 Warren task. Incorporate additional diagonal members that create denser triangular patterns. This design improves structural strength, load distribution, and resistance to bending, dynamic forces, and lateral pressure. It efficiently handles both tension and compression, minimizing stress concentration and reducing failure risk. With a superior strength to weight ratio, it is effective for projects requiring long span and high load capacity, widely adopted in the late 19th and early 20th century due to the advance in steel production and welding. It remains a preferred choice for railway, highway bridge, and modern construction.
As for the literature review, the double intersection Warren Truss Bridge is an advanced design of the original 1848 Warren Truss, featuring intersecting diagonals to enhance load distribution, stiffness, and structural performance for long spans. It optimizes material use by transmitting forces primarily as tension or compression, reducing deflection and stress concentrations. Widely used in railway and roadway applications. It outperforms simpler truss systems like Pratt and Howe in stiffness and load capacity. Modern improvements include high-strength materials and computational optimization, ensuring durability, reliability, and cost efficiency for heavy traffic and diverse environments. As for an example of double intersection Warren Truss Bridge in real engineering application, we have viaduct duplex. The upward viaduct is a railway viaduct allowing to Paris to Le Havre railway line to cross two branches of the Seine and the southeastern tip of Le-Lacroix upstream from Rouen, between Sotteville-les-Rouen, a commune on the left bank, and Eplet, a district of the commune of Bonsecours on the right bank bordering Rouen. It is a 356-meter long bridge which includes four metal spans in lattice girders with lower deck. Its width is 10.5 meters, which allows the passage of double railway track. It has three intermediate piers which is in the Cours Le Rhine arm, the second on the banks of Le Lacroix, and the last one the Preux Loops arm.
Moving on to analysis and calculation. For the analysis and calculation, there are several assumptions made and constant set. This is because we were not given any sort of bridge with values, such as the value of the members, the angle between the members, or the load given. For instance, the dead load is a constant that should be considered, where the dead load is the original weight of the bridge itself. Other than that, the live weight also is assumpted. Live weight is the standardized weight of vehicles and any body that is present on the bridge. Another assumption made is the absence of external forces towards the bridge, such as wind, and with these assumptions in play, the calculation concept can be done easily. The calculation itself is done by the method of joints and the method of section to ease the calculation process by parts to minimize errors. The method of joints is used to calculate the forces in the truss members by considering the equilibrium of forces at each joint, whereas the section method is done by cutting the truss into sections and analyzing the forces in the members cut by the section.
Now, I will discuss the double intersection Warren Truss Bridge, a structural design known for its efficiency and stability. This bridge uses interconnected triangles and double intersections, which make it ideal for long spans and heavy loads. Its design reduces shear forces and bending moments by evenly distributing stress across its members, making it particularly suitable for applications like vehicle and train bridges. Another advantage of this truss design is its symmetrical and repetitive structure, which simplifies construction. It also lowers cost to standardize fabrication while maintaining reliability. However, there are some challenges, including the complexity of its analysis and the potential for buckling in diagonal members under certain loads. In this case study, we analyzed the load distribution, reaction forces, and member forces of this truss. These findings demonstrate how the principles of statics are applied in real-world engineering scenarios, showcasing the practicality and effectiveness of this design. To conclude our presentation, the double intersection Warren Truss Bridge is highly regarded for its efficiency and reliability. It features an exceptional structural system known for its ability to distribute loads evenly and maintain stability under various conditions. One of its key strengths lies in its lightweight and modular design. This not only reduces material costs but also simplifies the construction process, making it a practical solution for engineering projects. However, it's important to note that while the design might involve some complexity in analysis, its advantages are undeniable. The bridge's capability to support heavy and dynamic loads makes it an ideal choice for multiple applications, including highways, railways, and pedestrian bridges. In summary, the double intersection Warren Truss Bridge offers versatility and practicality, cementing its position as a modern engineering favorite.
This is the example of reference that we use for our report.